Okay, yeah. Do we have to be on video or do we have stay on audio during the webinar?
We have to turn on video.
Yeah.
Okay, cool.
Perfect. So we are live right now. Okay. All right. So everyone, first of all, welcome to this very interesting topic called Maths for Machine Learning. I'm sure many of you would be able to take advantage of or benefit from this particular webinar, understanding how much maths is needed and how do you prepare for the same. Okay, so today we have Siddharth Gupta, who is a senior software development engineer at Amazon, and he's an aspiring scientist. He has created microservices API using AWS. It is rare to get an engineer who have a very good experience on building things, building systems on larger scale, as well as have an understanding of machine learning. And great, welcome Siddharth. Welcome to this session, and I'm sure that people would really appreciate your content. Now, I just want to tell a brief about. So this is briefly the agenda. What you see on the screen, that we'll talk about, give an introduction to machine learning briefly, and then we'll talk about need of mathematics for machine learning, mathematical concept for machine learning, and maths according to ML job roles. This session is going to be 1.5 hours approximately, and except for the speaker, everybody is on mute. And please use the YouTube chat to ask questions. The recordings and slides will be shared after the session, so no need to panic. If you want to take a screenshot, feel free to do so. And if you want to blog about it or write on social media, feel free to do it. And yeah, just mention that the content, the video or the screenshot is from CloudxLab. As long as you give the due credit, it's okay to use those slides or screenshots. All right. So yeah, so this is a brief about Siddharth, and we have talked briefly about him. So he's an SD2 at Amazon and has graduated from IT Kanpur. He's an aspiring scientist. He has created the microservices and API using AWS. So this is a very, how should I say, this is a very important topic, that how do you combine the machine learning with the software engineering and really well. At CloudxLab, our vision is to upskill engineers and IT professionals in deep tech, deep learning, machine learning, big data, DevOps, and make them employable and also future ready. So that's the core vision, and we have been able to do that on a larger scale. Lots and lots of people have taken our courses and have probably around 20,000+ people have been employed via CloudxLab so far. So this is the core value proposition that CloudxLab has. On the left-hand side, what you see is the content. On the right-hand side is the playground. On the left-hand side, you give the problem statement. We give the problem statement. And once you're done on the right-hand side, you click on submit, and it gives you a feedback saying how well you're doing, where you're stuck, and so on. And other than that, you get a fully functional access to the server where you can do anything you want, like the terminal. You can use here the big data tools, machine learning tool, MongoDB, and so on. The CloudxLab is basically online cloud-based lab. It is based on the real world, like the way if you join a top company, you will find a similar infrastructure there. It has a seamless experience and central data set and any device anywhere. That's the thumb rule. And you basically build your social profile, and that helps you becoming better at the career. Then we have a dedicated portal for jobs where you have where various companies keep on posting the jobs. the exam, right? So we conduct this exam called placement eligibility test, and the exam happen every 6 months. And whoever qualifies it, we basically place them. So the topic is maths for machine learning today, and I'll be handing over to Siddharth. Please go ahead, Siddharth.
Yeah, thanks, Sandeep. Thanks for the introduction. Should I share my screen quickly?
I'll stop sharing. And then you can go.
Sure, just give me a second. Let me keep the chat open. Yep, so hi everyone. Thanks, Sandeep, for the quick introduction. As Sandeep mentioned, mathematics is pretty important for machine learning, and today I'll try to cover, based on my experience, what I feel is the importance of mathematical concepts, and how they are utilized in machine learning, and basically what level or what depth of mathematics you need to have to be able to apply that in your particular role. So I'll try to cover all these aspects during the presentation. But before we start with how and why mathematics is important, since we have quite a varied audience, I would want to take this opportunity to give you a brief introduction to what machine learning is. According to Arthur Samuel, who coined the term machine learning, basically, it is the field where we give the computers the ability to learn without explicitly programming them. So think of the scenario of a usual software application. How it works is you have to specify very specific instructions to the computer, and that's exactly what the computer does. But what we want is that a computer should be able to learn on its own. Imagine a small child being born into the world, and how it perceives the world and learns about the world. No one tells the kid exactly what to do. It just learns by observing the world, by experimenting that, okay, if I leave something from my hand, it will fall on the ground. So I should keep it in my hand if I want to keep it, if I don't want that to fall. So that's how the kid learns. And we want the computer the ability to have that as well. The kid also learns from watching others doing stuff, and we want to give that ability to the computer. So it's basically like treating the computer as giving the computer a human-like learning ability. That's what machine learning aspires to be. And that being said, coming to the example, imagine like the kid grows up and starts playing Mario. How would the kid learn how to play Mario? How did we learn how to play Mario? We basically did that by playing with the remote control, trying to figure out the controls, or someone teaching us the controls, and then trying to figure out the game, that what control does what and what's the objective of the game. Someone just told us that, okay, we have to clear the levels. And that's what we did. We used to play, and we took a pretty decent amount of time. And at times we were used to save the princess as well. So can this thing be given to a computer? Can a computer learn this game to play by itself? Is what we want. What we want to do. But teaching the computer how to do this is not a trivial task to think, because there are so many controls. If you go ahead and specify the exact details that this is the button that needs to be pressed at this instant, it would be really painful. And the computer, you can do that, but it's not really a very good solution. It would just generalize to this game, and even if the game shifts by a frame or something, the program might mess up completing the level. So how can we do this? What do we need for the computer to, sorry about that. what do we need for the computer to be able to learn how to play Mario? How I would think is, how I think about it is in 3 steps, how the kid learns. First, you interact with the game. You try to play the game by itself. You press the different buttons on that you have. So that is like giving input to the world. Then when you give input to the world, you observe what happens in the world. You interact with the environment and you observe that, okay, when I press this particular key, this is how my environment behaves. If I press this particular key, this is how my environment behaves. So you go about pressing different, interacting with the environment and trying to figure out what exactly happens in the environment. And what do you do next? You just try to maximize the score. So you are given a concept of a score in the game and you try to maximize that. You either try to improve the distance that you have covered or the number of frames that have passed in terms of for a computer to think about it. It tries to count the number of frames that have passed, or it tries to maximize the time it is alive, or it tries to increase a particular score on the screen. So that's how it does. I'll show you a quick demo of how this thing works and how the computer learns. So we have a quick video about it. I'll just talk you people through it. So this is how the computer starts. It just keeps pressing random keys and the computer doesn't do a lot. I hope my video is visible. Now, after a few rounds, after spending some time with the game, the computer is able to move a few frames and try to do something, but still it doesn't understand the mechanics of the game. But after a while of training, this is computer just figuring out that, okay, this is how I need to proceed forward. It is not very good, but still it's a lot better. It is able to clear obstacles. It is able to kill creatures in the game and so on. So this is almost human-like performance, but this is not where it stops. It actually is able to beat human level performance or average human level performance, and even able to figure out some bugs in the game. This is because and this happens at a pretty quick speed. So you can see here that the Mario has exploited a bug here of the game wherein it just kills the owl and is able to proceed further. And this is not something that we might have figured out how to do that, but the computer can repeat this again and again. Now, this is another bug that the computer exploited, not going into the pit. So this is a game of Tetris, and to imagine how you would teach a computer how to play this is basically telling the computer, so how a scientist would have imagined how to teach a computer how to play Tetris is that the scientist would have given the objective to the computer to stay alive for as long as possible. Now, and given it the environment of Tetris. So the computer has the remote control to play Tetris and has the objective of staying alive as long as possible. That's a pretty good metric. That's how you win the game. Now, what the computer figured out here was pretty genius. It just paused the game and left it there. So you don't die, and the time you stay alive is just infinite now. So the computer actually figured out a way around figured out a loophole basically on how to go about beating the objective metric that the humans have given it in a way that it is able to optimize it, but still able to not do what we actually wanted it to do. So yeah, that also happens when we don't give the exact desired metric that we want to the computer. Ideally, it should have been the score, but as a proxy of the score, someone thought that, okay, time will also work, but that's not really the case. The computer figured out. So there are pretty good examples out there in recent research, wherein the computer has figured out ways to break the environment. Environment as in the environment it is interacting with. So maybe you've given it a simulated world or a small simulated space, but the computer figures out how to break break the rules that you have set for the computer and figure out a way to do things that we didn't really expect them to do. Just to achieve the objective that we have given them to do. So that's pretty fun to watch as well. Now, this being said, this is all the interesting stuff we can do with machine learning. Now, the question arrives, how do we do that? What is the skill that goes into making the computer learn all this kind of crazy stuff? The answer to that is our old friend from school, mathematics. It's the core of almost all the I would say all the machine learning algorithms, that it can automatically learn from the data and work with the data and make predictions the way we want it to. And every machine learning algorithm is nothing but just a mathematical concept coded up. So most of the any machine learning research paper that you might pick up would have the mathematical description and proof of why this thing works. And any model that uses it is just an implementation of that mathematical concept or an architecture built on top of those smaller mathematical concepts. So this meme summarizes it pretty well, that machine learning is nothing but algorithms and programming kept on top of maths. Now, the question arises why mathematics is important. Now that we understand that we need mathematics, why do we need it? And how much do we need it to understand machine learning? So, okay, yeah. Before I proceed further, I would want to point out that you guys can paste any questions into the YouTube chat, and I think someone from our team will be able to post them and forward them to me, I guess, on the Zoom chat. So feel free to do that, or you'll get the answers in the YouTube chat itself. Okay, continuing, why mathematics is important. So to think about it, you need mathematics. If you have an understanding of mathematics, you will be able to figure out the right algorithm, and you will be able to figure out how to tune that algorithm. So think of a scenario where if you don't have the understanding of the underlying mathematical concepts for machine learning models, it would be very difficult to figure out which machine learning technique to apply for a given problem. So for instance, if you have a problem, say for your business, so you own a business and you want to figure out who is a good customer for your business versus who is a bad customer for your business. So you have a database of customers that you have worked with, and some of them have just been bad customers for you. They have tried to dupe you, or they have tried to cheat you. They have not been good at paying back or something like that. So there can be some small number of bad customers which pose risk to your business. Now you have their data, that what kind of things they have purchased with you, and what's the price is of the products that they purchase, and those kind of things. Now you want to figure out if any potential future customer is a good customer or a bad customer. Machine learning can do that. It can identify that based on a few data points that might be indicators of that. But how do you go about that? If you want to do that, you will have to have the basic understanding of that. Okay, this is the classification problem. We want to classify between good and bad customers, and how do we? What kind of models can work with it? And it's not just about finding the right algorithm. It is also about understanding the data, that, okay, this is the kind of data that I have, and these are the kind of models that will work with my data. So consider the scenario where these days deep learning is pretty common, but to train a new, fresh deep learning model from scratch would require a huge amount of data. So there are techniques to reduce the data as well, but in most cases, if you are training it from scratch, it would require a very huge amount of data. And in most cases, data is the limiting point for most machine learning applications that we don't have either enough annotated data, or we don't have a lot of data in the first place itself. So that being said, if we have an understanding of the machine learning, the mathematics that's going on underlying, that how many parameters are being tuned for this particular machine learning model, we will be able to judge that how much data do we need to tune these parameters. Now, coming to the next point, if you understand the mathematics, you will also have an understanding of the algorithm that you would need, as I told in the first point as well, that if you have, say, you understand that this is a classification problem. Now, you have picked up an algorithm, and the algorithm, you won't be using the algorithm as is. If you understand the mathematics underlying it, you can actually modify the algorithm. So a machine learning model is nothing but a sequence of mathematical functions placed in conjunction to each other. So there are a bunch of mathematical functions, and the output of the first function is fed into the second mathematical function. The output of the second function is put into sent as input to the third mathematical function, its output to the fourth one, and so on. It's just a huge sequence, as well as parallelization of multiple mathematical functions. Now, if you do understand the underlying mathematical functions for any machine learning algorithm, you can also tweak them. That, okay, if you want the model to output a probability at some stage, you tweak the mathematical function to output a you swap it with a function that can output a probability, or you can put in a function that does that. If you want to, so there are basically different kinds of mathematical functions which have different behavior, and you can swap them in the algorithm as you need. So those are the, so mathematics is important at that level as well, if you have that understanding as well. And now that we have the model, analyzing the outputs provided by the model, that how good your model is doing. So consider the good and bad example, the good customer and the bad customer example. Now, if you need, if you suppose you have trained a model that is able to identify a good customer versus a bad customer. Okay, yeah, between a good customer and a bad customer. And think about the scenario that your model has started predicting that, and how do you figure out how good your model is performing? Will it be the accuracy of the model? Will it be the precision of the model? Will it be some other metric that you would want to evaluate? So think about, if you don't understand it and you just go about where the general accuracy of the model, that how many, if it is trying to identify good people, or it is trying to identify bad people, what percentage of bad people, or what is the percent of bad people it is able to identify? Yeah, or what percent of people it has identified as bad people are actually bad people, those kind of things. So there are a bunch of different metrics, and it's not necessary that you will be able to choose the right metric out of the right away, or without having an understanding of the mathematics that's underlying. So it's just basic statistics that you need to have an understanding for. And the last point is what data pre-processing techniques to use, because if you have an understanding of the machine learning model and how it manipulates the data through its algorithm, you would also be a better judge that, okay, this is how I need to frame my data. Because if there are algorithms, if you have a lot of data, you can just pump the data in a raw format into the machine, into the deep learning, into the deep networks. that are there. And the model does this job by itself of pre-processing the data. But if you don't have enough data, then you can't just dump all the data as it is into the neural network. You'll have to use a smaller, some classical machine learning algorithm, and also figure out how to pre-process your data to make it numerical, so that the data is consumable by the machine learning algorithm. So imagine that you have the ages of your customers. You would not want to just put in the ages as is, because at times it's better to just classify them, that under 18 is one bucket, above 60 is one bucket, and all the ages in between are bucketized into, say, 5 years of it. So 18 to 25 is one, 25 to 30, 30 to 35, and so on and so forth. So that's how you have to think about how to pre-process your data, so that and you will be able to figure this out, that okay, this is how the algorithm will improve only when you have figured out that this is how the algorithm works. These are the mathematical concepts that it uses. And the last point it is, if you are going for a research-based role, having a very good grasp of mathematics is really, really important. You can't just go about because in research roles you are trying to push the boundaries, and you really can't do that without having a very good grasp of the underlying basics and mathematics of machine learning algorithms. I'll take a quick question. I think Sachin has posted on my chat. KMSum has asked, what are the typical challenges that beginners of ML face? To answer that, I feel it depends on at what stage of a beginner you are, to be frank. It's more like that if you are just starting and you're just trying to enter the space of machine learning, the most difficult thing would be the overwhelming options that you have. So these days, a lot of machine learning has been democratized. You get ready to use libraries and ready to use models out of the box that you can use for your problem. And making a choice there is something that beginners really struggle at. And I feel the realization that it is not the machine learning model, but the data that is important, the most important thing for your machine learning application. Reaching this realization is where I think the difference between a beginner ML practitioner versus an intermediate ML practitioner comes. That you stop focusing on what model to use. You get an intuitive feeling, but you start focusing on how to get cleaner data, because real world data is never completely clean. It is always either the labeling would be off, or you won't have perfect data in the real world. So those are the things that I feel we initially struggle with as beginners, but as time progresses, I think you get an understanding of how the models work. That's where mathematics is important. That you should get an intuitive feel that okay, this is the kind of model these are the kind of techniques that can work for my kind of problem. And you start eliminating that okay, this won't work because of this reason, this won't work because of that reason, and you try out the remaining shortlisted techniques. And then you figure out, okay, it is not the techniques that I have to work with, it is the data that I have to work with to get better results now. But yeah, I hope I answered the question. Shoot it again if there's something else. Cool. Coming back, the next point is coming to the next part. Now that we understand why mathematics is important, the next question would come to you is how important is mathematics for me, considering we have an audience which comes from a variety of roles. We don't have just all people from a single role. We have people from multiple roles. So to understand how important mathematics is for you, it depends, which is a usual answer, I think, for most questions. And it depends on the kind of role and what you want to do with the ML models and how involved you are, at what level you are involved with the machine learning applications. So how I think about it, based on my experience and my understanding of the industry, I have seen the knowledge being bucketed into three major buckets. The first one being the researchers in the industry, or even in academia. So researchers are basically scientists who develop new architectures, who are trying to push the boundaries of machine learning, of what machine learning can do today, and trying to innovate on new architectures and new types of models and new algorithms in their day-to-day life. So to be able to do that, you need to have a really, really good grasp on the basics. And you should have a very good intuitive understanding of the machine learning, different architectures and different models that are out there, why they work and how they work, to be able to push that. And to do that, you really need to have a good amount of comfort with mathematics to be able to derive things and reproduce the logic for already existing models, and to add things to those architectures. The second category is that of practitioners, or you can say engineers, basically. These are the people who use the models and architectures that have been developed, and they use them for the real world applications. So imagine any application. So suppose you do a quick search on YouTube. The algorithm behind is actually a machine learning algorithm that searches that for you. A better example yet is your YouTube feed. The recommender system gives you a bunch of videos that align with your interests, based on what you've watched in the past and based on your activity and searches, to what you would want to watch next. So to build those kind of things, you really don't need to go as far as pushing the boundaries of machine learning, but you just utilize the models that have already been developed by the researchers. So to do that, you don't need a very strong grasp on being able to reproduce the machine learning algorithms or recreate them from scratch, but you do need to go through what the scientists have done, what kind of mathematics they worked with, to be able to understand that, okay, this is at high level what the algorithm does. It tries to optimize this kind of a metric. These are the kind of processings functions that it applies on my data. And this is how it generates the output, whether it's a probability, whether I can consider the output as a probability, whether I cannot consider the output as a probability, and those kind of things. So you don't really have to have a very strong reproducible kind of thing for machine learning models. You just need to have working knowledge that, okay, these are the high level concepts that are being used in the model. That being said, coming to the third category of roles that I've seen, which are more like product roles, that these are the people who basically bridge the gap between the tech and the business. So when you're trying to develop a machine learning algorithm in the industry, you're trying to solve some business problem. And in most cases that I have seen, at least, I would not say that is true in general. In most cases that I have seen, the tech people and the business people are not really on the same page. They need something to be on the same page in between. So that's where, because it's very difficult to, if someone is not from a tech background, it's very difficult to explain them what are the challenges and what are the things that are available in a machine learning for them to use. And for business people, it is very difficult to ask from machine learning practitioners as to what do they need from them. So the product people basically bridge the gap. They translate the tech to business and business to tech based on what the business needs and what machine learning can offer. So at that level, you need to have an understanding of not the core mathematics of the algorithms involved, but at least the high level understanding of what algorithms can do. And apart from those high level understanding of the algorithms, it would help if you have an understanding of how to evaluate those algorithms. What are the metrics that you use for evaluating different kinds of algorithms? That so, for example, our example of good and bad customers, as we take. If you have an understanding of that, okay, we don't want our algorithm to. It is okay for our algorithm to miss out a few bad people from being identified, but we don't want too many good people to be identified as bad people. So this can be a business requirement that you don't want to put a lot of good people through scrutiny. Even if you are letting a few bad people go, you don't want all the good people. You want as many good people to be not classified as bad people as possible. How do you do that? So this is a business requirement, really. Now, to translate it to tech or to be able to judge how good the model is working on that aspect, you need to have an understanding of measures of machine learning models. How do you evaluate them? So in this particular example, we don't want too many good people to be identified as bad people. So there's a metric called false positive rate, which does that you're trying to identify bad people, but how many of them have you identified as false positives? So it's just a fancy term of a very simple fraction that is created. So it's not very complex mathematics, but still it's good to understand what different options you have for evaluating different ML models. Now, that being said, let's now that we have cleared the why and the how and the what's, I would want to jump into the next part, which is trying to cover what different topics from mathematics do you need to be able to get this understanding, get a grasp of these machine learning techniques and algorithms. So most of the algorithms out there really okay. Before we get into this topic, I just want to check if do we have any questions, Sachin, or can we just continue? Okay, cool. We can continue. Cool. So based on the so coming to the mathematics, we basically have four major categories or four major topics that we need to be really comfortable with to be able to understand the underlying mathematics, that how the models are working and how do they perform and how do we evaluate them and how can we pre-process the data and those kind of things. So they are basically, as we see on the screen, linear algebra, calculus, probability, and statistics. So not all of them would be needed at the same depth for all the rules that we just saw. But I'll try to differentiate between how deep of a knowledge you need in each of these topics to be able to have a comfortable grasp for what you want to do with machine learning. Sorry about that. So this basically is a rough pie chart, you can say, of how much of each topic is involved in day-to-day when we are working with machine learning. So majority of it is just linear algebra, which is nothing but working with matrices, tensors, vectors, and those kind of things, and basically just manipulating data, multiplying things, adding things, and those kind of things. The second largest chunk is probability and statistics. So you need to have a good understanding of how probability works and be comfortable with those kind of things, that, okay, this is how you sample things and this is how sampling works and this is what sampling means and those kind of things. And statistics would include, as I said, you would need to evaluate different machine learning models, compare them. So you need statistics for doing that. Then comes then the remaining part is covered by basically calculus and algorithms and other such smaller concepts. Algorithms are important because we also want to make sure that the algorithms that we choose, they are optimal for our use case. The data that we have, the time that we want the algorithm to take, the time complexity of the algorithm, how much memory does the algorithm use, and those kind of things. So that is, so these are basically the depth at which you would need. I'll try to cover that in more detail as we go on. Now, so the first topic being linear algebra. Linear algebra is nothing but the branch where we deal with matrices, tensors, vectors, and those kind of things. And we try to solve linear equations. And how do we represent things as linear equations, as matrices? How do we manipulate them and those kind of things? So this is pretty basic stuff. And the reason why linear algebra is important is because computers are, think about how computers process things. These days we have a bunch of CPUs in our a bunch of cores in our CPUs. And if you are doing really intense ML development or ML application, we also use GPUs. Now, what do these hardwares do? They are nothing but, so GPU is nothing but a huge number of small processors. So not very powerful processors, but a huge number of processors. Now, what can these processors do? We can dump a lot of data on all these processors, and all of them can evaluate, say, one example from a data set. So how your data set would look like? Your data set would look like, so suppose you have the data set of all the customers that you wanted to classify between good and bad. Now, the data you would have is every row. So imagine organizing that data into a matrix. It's just a sequence of rows and columns. Every row would correspond to one of your customers, maybe. Now, what would every column correspond to? Every entry in each row. So the first entry in your row can correspond to what age bucket they lie in. The second entry in your first row can correspond to what are the purchases that they have done. Now, third column can correspond to what are the prices at which they have purchased things, and so on and so forth. So it basically becomes this three-dimensional thing that you want to create, and you want to put that into the ML algorithm. Now, how do you go about doing that? And why do GPUs work better with this? Because now every row that you want to push through an entire pipeline of mathematical functions, as I said, ML algorithm is nothing but a sequence of mathematical functions put up one after each other or in parallel to each other or something like that. So some arrangement of mathematical functions. Now, to do that, what you need is you want your data to pass through this entire layer. And to do that, GPUs are very efficient. For every single data point or data row in your training data, that can be passed to each of the cores in the GPU, and then that data can just filter through. So that's where the true power of matrix comes in, that you can actually push a huge amount of data very quickly. Otherwise, if you do that one by one on a single processor with one example at a time with just a vector of numbers, it would take really long for us to develop the kind of models that we have developed now. So yeah, that's basically the reason why there are so many matrices and so much of linear algebra involved. But it's nothing but just a fancy way of saying that this is how I deal with a sequence of numbers, and nothing too complicated than that. Now, coming to the use cases, that is, in what scenarios do we use linear algebra? As I mentioned that, I explained where matrices are being used. Now think about the scenario that, okay, matrices are being used in these kind of, that because they are being used because of the GPUs and the multiple cores that we have. Now, you cannot develop an understanding without having a grasp on how are my matrices being manipulated, and what kind of manipulations or what kind of operations are being performed on my matrix, and how can I optimize it, and what are the core functions that are being applied on my input data set, so to say. So if you have that understanding, and to build that understanding, you really need linear algebra. You would need to have an understanding of matrices, how to manipulate equations, basically, so to say. So this is, so to think about, okay, I'll come to the roles later. I'll just try to cover the complete aspect of linear algebra first. So yeah, coming to the next point, we understand that, okay, this is what linear algebra constitutes of. And yeah, as I said, vectorization is one of the indispensable concepts. That is, if you don't vectorize, vectorization is nothing but putting all your data into a form of matrix. And vectorization will basically parallelize all your computation. And without vectorization, the time it would take for a machine learning model to get trained or even infer on a batch of data, that would be really long. Vectorization does that pretty well. And how do you vectorize it? You just basically stack them on top of each other, and that's where linear algebra again comes into picture. And to talk about a few techniques that involve machine learning, involve linear algebra, we have dimensionality reduction, we have data visualizations, and we have examples of convolution. So convolution is nothing but a type of neural network wherein so convolutional neural networks are really good at processing images, and images are nothing but huge matrices of data. They are like, or you can say even a huge tensor of data. So you have a bunch of pixels in the image, and each pixel can be seen as a combination of three numbers, which are red, blue, and green, RGB, the three colors that make up that particular pixel. So imagine that a picture in itself is a matrix, and then you have three colors stacked back to back. So an image in itself is like a tensor now. And to stack a bunch of images in your, to vectorize on images, that makes it a 4D tensor now. And to manipulate on those kind of things, so convolutional neural networks basically are really good at manipulating images, extracting information out of images. And that's again one place where linear algebra comes in hand, that how do you apply a small matrix on top of a larger matrix to get the convolutions out of those, and how do you filter them, and those kind of things. So it's all just simple, very simple operations if you get to the core of it, but you need to have a high level understanding that, okay, these are my options available when I'm building. So if you want to build an image processing ML application, you would want to have an understanding of these topics, and for understanding these topics, you would need linear algebra at the base of it. And coming to the concepts that we have in linear algebra that people would want to be familiar with for working with machine learning, you would start with very basic scalar, vector, the different kinds of components that we have, and that we deal with in linear algebra. So those would be scalars, vectors, matrices, and tensors. Now, the second would come as what are the operations you can perform with these entities. Those would be different kinds of matrix operations, multiplications, transpose, how do you find an inverse, how do you decompose, and those kind of things. So just understanding the properties of matrices, there are a bunch of things that you can do with matrices very well. You can, so imagine how we factorize numbers. we know how to factorize the simple numbers, the scalars that we have. We can factorize them into smaller prime numbers. Now, there is something similar that you can do with matrices as well. You don't break each number of the matrix, but you try to break a matrix into a bunch of matrices which have very specific properties. That the first matrix would just be a diagonal matrix. The last matrix would just be a transpose of an identity matrix or something like that. So you can have very specific kind of things that can actually make your computation much, much easier. So to have that level of understanding, it's good to have a good understanding of linear algebra. Then the third and fourth topics are basically very specific. Principal component analysis is a specific machine learning technique, which is basically used for when you have a huge dimensionality of data. So imagine that you're trying to feed a classifier with the age of your customer. Now, age can be a huge number, and you try to bucketize it, so there are a huge number of buckets. So that creates a huge number of features. So this is just one feature being split into a large number of numbers, which are mostly 0, and a few numbers are 1 in between, because the age of the customer would fall into just one of those buckets. Now, that can cause the dimensionality to increase. So if you understand the machine learning algorithm, you'll realize that, okay, if I give it too high dimensionality data, the machine learning algorithm might not be able to work as good as we want it to. How do we deal with it? We try to reduce the dimensionality. We try to find out what are the correlated features and how can we reduce the dimensionality. So that's where principal component analysis comes into picture. It's a technique wherein it allows us to figure out what are the primary K components that we want to take out from our data set that will represent most of our data set as is. So that's and most of that involves linear algebra. You would be dealing with matrices and their decomposition and those kind of things. And SVD is also singular value decomposition is also another. It is an important aspect if you try to understand it, but depending on the role, you might want to. You might be okay just skipping it because it's really at the research level, but it's good to have an understanding of what SVD does. That when you're trying to solve the least squares regression problem, you can get a closed form solution using SVD. So what SVD does and how it is used, that's how it comes into picture and how it comes into importance, basically. So that brings us to the end of linear algebra concepts. And to briefly summarize that, if you are at a research level, you would want to have a very good grasp on almost all these concepts. If you are a practitioner, you would want to have an understanding of these concepts. If you're not very rigorous, that's okay. But you should basically understand that, okay, there is a closed form solution for least squares regression, which comes from SVD. What SVD does, it's okay if you don't really have a very good grasp on that because you don't really use eigenvalues and eigenvectors day to day. And you should have an understanding of what PCA can do and what kind of thing. So when you're reducing the number of features in PCA, principal component analysis, you are losing out some information. You can't expect it to retain all the information that you had in your input data set. Now, how do you decide that what's the optimal number of reduced dimension, that optimal size of the reduced dimension that you would want to go with? So for that understanding, that is something what a practitioner would want. That, okay, I have this real world data, I want to reduce it. I know that PCA can do it, but I don't know what's the reduced dimension. So if you have an understanding of the underlying mathematics of PCA, you would know that, okay, this is this. So there are a bunch of metrics that PCA algorithms, the libraries that have PCA algorithms emit. And to make sense of those metrics, you would need some basic level of understanding of what's the underlying mathematics of PCA. So that's where I would say the practitioner level of things would be that you understand the mathematics underlying. And for the product person, you just need to understand that, okay, there is something happen. You need to understand that there are matrices being pushed into a huge network, and this is how the network propagates them forward. And these are the kind of metrics that you get at the end. It is outputting a probability of something and those kind of things. So you don't really need to have an understanding, a very good grasp on the core basics of linear algebra, so to say. You can go ahead, work with, but you should understand that what matrices are and how do they get manipulated and those kind of things. So I would say the basic high school or intermediate level understanding of things. Cool. That brings us to the end of linear algebra and coming to the next concept that we would want to cover today, which is calculus. Calculus is something I feel that people who have a non-mathematical background sometimes get intimidated with. But I don't really see a reason unless you really want to get deep into it. That's when you want to have a really, really good understanding of calculus. So to introduce calculus, it is nothing but the rate of change. It is just studying the rate of change of different things. That how does something react to when I change the input by a bit? So imagine the computer learning Mario in the demo video that we saw. What was the computer doing there? It was trying to understand that, okay, if I press this particular key by this duration, this is what happens. And if I increase the duration of pressing this key by this much, this is how I move. And it tries to identify whether it moves towards the target or away from the target goal that it has. And it tries to optimize that. So how does it do that? So suppose you are trying to figure out a way down a particular mountain. You want to get down as quickly as possible. So you will take the path that is the steepest because that's the quickest path down. So that's what it is, that it is the steepest path is nothing but the direction in which the rate of change of height is the maximum. And that's the direction that you take. Now, think of what the computer would be doing with Mario. It would be trying to figure out the direction wherein it can make the most progress most quickly. Otherwise, you would just be getting stuck in some particular. So how we saw it initially, it was just stuck. It was not able to move at all. So it figured out the direction or the direction in which it would, if it moves, then it will get the maximum progress. And that's where calculus helps us. It tries to minimize the error. If we are going in the wrong direction, calculus tells us, okay, that this is the wrong direction. This is the way up. We need to go down. And we need to go in the opposite direction. This is the wrong way that you took. So it is kind of a feedback from the thing. So it is kind of reducing the loss. And that's where you need calculus, so to say. And the kind of things that where we use calculus are basically it permits us to understand the optimization process of machine learning algorithms, that how do they internally optimize things. When we push data forward, there is no calculus involved. But so when we are doing an inference, it barely is any calculus in most of the cases. It's just pushing your data and applying a bunch of mathematical functions and getting the data out. Now, the problem comes when we are training the machine learning algorithm. When we train the machine learning algorithm, we have a bunch of parameters that we have said that we can. So parameters are like knobs in the machine learning algorithm that we can tune, that the computer tries to tune. And there are some knobs that we tune as well. But these are the knobs that computer tries to tune to make a model that, given the input, it will get the desired output. Now, how does it know which way to turn the knobs? Now, to figure out the direction in which way to turn the knobs, it pushes the data through the sequence of functions, and it gets the output. And then it compares the difference with the ground truth, the true output that we want. that, okay, this is the output that we expected from the model, and this is the output that we got from the model, and this is the difference. And then we try to propagate this error back. And this propagation of error is something that involves calculus now. So if you want to understand that internal working, that how this error is being propagated and what is exactly happening, that's the place where you need calculus. And that's what the algorithm that I just described, propagating the error back, that is back propagation. And one other very important algorithm is gradient descent, which is basically the algorithm that I was describing right before this, that you find the direction of maximum slope to reduce the error most quickly. And that's what gradient descent is. The meaning of gradient descent is that you want to descend in the direction of the gradient. Gradient is nothing but the slope of or rate of change of something. So you want to move in the particular direction, and that understanding that requires calculus. Now, designing cost and loss functions. So cost and loss functions are nothing but how do you signify error? So your machine learning model outputs something, and you have the ground truth. Now, to be able to find the error between those two, you need some function that is an indicator of the loss, that how badly the computer did, or how well the model did, or how badly the model did. So those are basically cost or loss, called cost or loss functions, and we have a very precise way of choosing them so that we don't give a wrong objective to the computer, because computer would try to minimize the loss or reduce the cost function. So that's what it's trying to optimize. And as you saw in the Tetris example, if we give it a wrong metric to optimize for, the computer will not do what we actually wanted, but might figure out a way to do something else. So that's again where something where calculus is involved, because when you build a loss functions, you have to propagate the error back, and you need to know how to differentiate that function and those kind of things. I'll cover what level of knowledge is needed at each level a bit later. Then again, back propagation is what I described, propagating the error back into the network. It is a very common technique that is used, and it is the technique that is used in almost all the neural networks that we have. And it is basically just pure calculus that derives it. Now, coming to the concepts, what are the concepts involved? Now that we understand where it is used, what do we need to learn in calculus? The things that we need to learn are basically derivatives would be the basics, derivatives and integrals. So derivatives are nothing but the figuring out the rate of change of slope at some place, and integrals are nothing but they give you a way of reversing the derivative. If you want to go to the function from where the derivative came from, that's what integral is. And it, in terms of graph, there are different interpretations of it. It also represents the area under the curve and those kind of things. But I think for machine learning, we can stick to reversing the derivative, I think, if I'm not wrong. So considering derivatives, we would need the basics of derivatives. How do we work with derivatives on matrices? That's another. So combining calculus and linear algebra, because we actually have matrices being passed through the neural networks or any machine learning algorithm. And if you want to propagate them back, we would want to differentiate or find the derivative of something with respect to the matrices. So you should have an understanding that this is what is going on when you're propagating something back. Then you should have an understanding of what gradients mean by intuition. That, okay, so you would only be able to observe when you're training the model that this is how the gradient is going and this is how my loss function is going. And you're trying to optimize that. So how do you go about doing that? And to understand that what does this number actually mean, you need to have an intuition of calculus. You need to have an understanding of calculus and an intuition of gradients. Then the next thing you would need are basically optimization. When you want to reduce the error or reduce the loss function, you're trying to minimize the loss function or minimize the cost function. Now, how do you do that? Again, you're trying to differentiate it and find the minima or the maxima of those functions. Now, And this is where it leads to the point that why do we need calculus for knowing what kind of loss functions we can use? So to understand what kind of loss functions we can use, we need to know that not all functions have a maxima or a minima. There is a special class of functions that we can use, which have that kind of property and are differentiable. And those are called basically convex functions, which have a single optima, and those are the functions we would want to use to use as cost functions in most scenarios. And then there are things like convergence and divergence. These would be sort of advanced topics, wherein you would want to understand that what kind of functions are actually convergent and those kind of things. So basically, you try to you want to choose the right kind of function to be used as your loss function or the cost function. You don't want to put any function as a cost function and try to optimize that. So trying to choose that this function will work better for my particular problem and this function won't. For that understanding, you need to have a basic understanding of calculus. Now, coming to what level of understanding we need for each role, again, you would need, so being a researcher, you need to have a good understanding that's understood. For a practitioner, it's good to have an understanding of most of these concepts at a high level. If you can't reproduce it, you should understand the concept as such, that this is what maxima and minima mean, and this is what I do in terms of calculus operations to find the maxima and minima. And so you need to understand gradients. There are very basic issues with gradients when you're training machine learning models, like your gradients just go to zero or just go to infinity because of some reason. How do you regulate that? What is the cause of that? What can I do to change those kind of, what knobs do I turn to manipulate those things? So those are the kind of things that you would need for understanding. So that is the level of understanding that you need to have with calculus if you want to be an engineer, be a machine learning engineer. Now coming to, or even a data scientist or at that level. But if you're coming to at a product level, what you would need is you would need to understand that, okay, there is some kind of optimization that is going on, and there is this is how the optimization works. And if someone gives you that, okay, this is the kind of error, this is the graph of the train validation loss or those kind of things, you should be able to understand those things. And to be able to understand those things, you need to understand what how are errors computed, what, if not the core mathematics, but at least get an intuition of what the underlying concept is, to be able to make sense of that data if you want to bridge the gap between the tech and the business. So that brings us to the end of calculus. Coming to the next part, which is probability. Probability is the branch. So I think most of us would have had some intuition of probabilities when we deal with chances, or when we are dealing with betting, or when we are dealing with predicting something, that, okay, today we say that there is an 80% chance that Team India will win cricket match. So that's just us trying to figure out what the probability is. So to have a good grasp on probability, it's very important. Sorry about that. It's very important to have a very good grasp of probability, and to understand how we can combine different probabilities and those kind of things, and what are the properties of different kinds of probabilities or different variables that we play within probabilities. So that's how it's important. I'll try to give a few use cases how probability is used in machine learning. So what I would say is, if you want to understand, you need to understand probability to make sense of the output of machine learning models, basically. That, okay. So yeah, the first point being that machine learning, as I said, probability is sort of a human common sense, that you get a basic hunch that this is the approximate percent, or this is how likely something is expected to be. Then the second aspect is basically that, so as I gave you the example of a good customer versus a bad customer, that is a classification problem. Now, what your model would output is a probability that given a input data set, this is how probable a particular person. So given a person's data as input, this is how probable that person is a bad customer. Now, if that person, now you have to put a threshold, you need to put a bar on that. Okay, if the probability is above 0.75, I will definitely call this a bad customer and not let them interact with my business. But if the probability is less than if the probability is less than 0.5, I would definitely consider them a good customer and let them easily work with my business. But if they are somewhere in between, I might want to have tight scrutiny on what they are doing with my business, so they don't dupe it, because they are on the verge of becoming a bad customer. So you need to have that level of understanding of probability and how you work with things. And also, to develop machine learning algorithms, there are algorithms that get developed completely based on assumptions on probabilistic distribution of things. So naive Bayes classifier is one such machine learning model, which basically just uses, it starts from scratch with a probability density function. And from there, it finds a closed form solution for building a machine learning model, that this is how your entire data set will behave, and this is what the ML model needs to learn. So there are a bunch of parameters, the parameters of the probability distribution function that you want to learn from the data, because you don't really know you understand that this is how my distribution would look like. So for instance, we would have come across the bell curve. The bell curve is nothing but normal distribution. And most of the things in nature fall into the bell curve, that on the extremes there would be very small populations, and in the center there would be a huge mass of populations. And the bell curve would basically, the normal distribution is basically how you would want to model your data set as well. Now, to model your data set as a normal distribution, you would want to find out the parameters for that normal distribution, particularly the mean and the standard deviation. So you need to understand those kind of concepts, that, okay, these are the kind of probability distribution functions that I have available with me. And that's how these classifiers have been built. And what is the underlying, so naive Bayes classifier offers you a bunch of distribution functions underlying it, if I'm not wrong, yeah. And based on that, you try to, and you need to have an understanding of how those functions behave to be able to use these classifiers. Now, if you have an understanding of those, that, okay, this is how my population looks like, and I would want to model it using this kind of a probability distribution functions, hence I will use this kind of classifier on my data set. Those are the kind of decisions you need to make when you're choosing a machine learning model, and understanding of probability comes in help there. Now, yeah, probabilistic loss functions, as I said, that you are basically the output that your model gives out is basically just a probability. Now, you use a loss function on top of that to figure out what's the error. So that's again somewhere another area where you need to have an understanding of probability to be able to choose the right kind of functions. And yeah, then there are different kinds of different concepts in machine learning space, wherein you need to have understanding. For instance, if you want to sample from a data set, you would need machine learning. You would need the knowledge of probability with you. That, okay, this is how I sample from probability distribution. Information gain is another important metric in decision trees when you're trying to
split based on a particular feature. So you need to know that which particular feature will give me the most information gain. And that again comes from a concept of probability, that this is how it distributing on this particular feature splits my data set, and this is the probability that I will find a good versus a bad person on my right side, and this is the probability that I'll find a good person on my left split. So that again gives you some, and that happens just in a tree kind of format. You just keep splitting every node on some particular feature. So that's something where information gain comes into picture, and you need to have an understanding of probability there as well. Another thing is ROC, which is I think it's an operator curve. I'm forgetting the full form of ROC right now, but it's a very common metric that is being used. I think it's repeater operator curve, if I'm not wrong. Sorry about that. You can Google that. ROC is something that basically gives you the performance of the model, that this is how confident the model is for different particular values of recall, or for different values of precision. And that's something you would use to set the threshold. So for instance, we discussed that the model is giving the output. ROC is, thanks Sandeep, it's receiver operating characteristic curve. And it gives you the output so your model gives you the output of a probability, and you want to set a threshold on that probability, that this is the point where I would classify the people as bad customers, and this is the threshold where I would classify them as good customers. To be able to decide that threshold is a very important metric, because that will affect your final end goal or end utilization in your business, basically. So that's something where you need to have an understanding of what these ROC curves mean and how did I use them to figure out where I need to put my threshold. So those are the kind of things and concepts that you need to understand from probability point of view, that this is how I use probability in my day-to-day life. Now, coming to at a role level thing, I think you can on yourself as well get an intuition that how deep of an information you want, how deep of a grasp of probability you want to have for your own personal use case. So researchers would need to work with all these things in depth. Practitioners can work with basic understanding of how these things work, what kind of functions they have available with them, and what are the different options that they have available with them for choosing probabilistic models and or loss functions. And how does information gain work, for instance, if they want to. So when you're designing decision tree, you would want to understand the concept of information gain. So those are the kind of things that we would need from at a practitioner level. Now, at a product level, I would say, or at a managerial level, you would need information about how the ROC curve works, because that's where you want to decide from a business perspective that, okay, this is where I want to put the threshold. And you would want to communicate with the team in their language. And you would want to, even if you want to develop a model on your own, you would want to, so there are a bunch of no-code setups that are provided these days. So to be able to use those setups, if you want to use those setups, you would want to have, if not a complete practitioner level knowledge, you would still want to have a decent understanding of what's going on under the hood, so that you can tweak them, you understand that tweaking what parameter does what, and those kind of things. So there also you would need basic understanding of probability, that, okay, this is what this particular thing means, and this is how I deal with it. Okay, we also have, I missed about that. We also have the concepts that we want to cover. I'll cover these. So you would have the basic probability that we all study. You would also want to understand the random variables that we have, which are basically understanding how you deal with variables. So building a science on top of probability. What we study probability at high school or intermediate level is just figuring out how probable a particular event is in terms of specific numbers. But we can also generalize it. We can build probability mass functions and probability density functions on top of that. And there are a bunch of different kinds of distributions. And as I mentioned, you would want to know different kinds of distributions for choosing what kind of particular model you would want to pick for your machine learning applications. As I said, that so these models like knife-based classifier and these probabilistic models, they are completely derived from probability. So they also go through, so we also apply a process called maximum likelihood estimation, which is nothing but trying to optimize that, the point where the parameters for that particular distribution, where it would most likely represent the distribution of the data set that we have. So so again, maximum likelihood estimation and error minimization, all these come into picture at that point. So you need to have a grasp over probability and calculus and linear algebra at that stage. Then there's Bayes' theorem that we need to have an understanding of. That is also pretty important when you're going for sampling or even when you're developing regular probabilistic models. Information theory, as I mentioned, what it is, I've already mentioned here. Information gain is part of information theory. So information theory entails a bunch of other things as well. It's good to have an understanding of that. And sampling methods is something you would want to brush up on at least, if not really go into deep. Sampling methods are basically useful when you're using generative models that you want to but you should, in any case, I think you should have an understanding of how different sampling methods work, how you can sample a random data point from any given probability distribution function. So yeah, I think I've already described at what level of depth you would want to go for for different roles. Now, coming to statistics, statistics is, I think most of us again would have already been introduced to it in one way or the other. It is nothing but trying to get a summary of numbers in one way or the other. We try to draw some conclusion from the set of numbers that we see in front of us. And to do that, we can't really comprehend a huge set of numbers. We need some concise form of numbers. So that's basically what machine learning is doing for us. It is taking a huge set of numbers and it is trying to, using a large set of data, it is trying to consolidate into a single number, that this is the probability that this particular thing is good or bad, or anything else that we want to predict with machine learning. So that's what it is doing. So this meme basically gives you a good summarization that statistics put into in a very fancy way is machine learning. But it's sort of, so this is kind of an ongoing debate whether machine learning is just only statistics or is it something more than that. But yeah, this is how it works. So machine learning, it is just statistics, and when the level of statistics we want to work with, it depends on what we want to do. For instance, when we are trying to visualize different data sets, or we are doing data exploration, we would want to, so for instance, we covered principal component analysis. So what principal component analysis would be doing underlying would be trying to figure out what particular features are correlated with each other. So these correlational things are computed using some form of statistics, that, okay, these two features have this kind of a correlation value, that is just a statistics. You're summarizing the huge set of numbers into a single number, saying that this is the correlation between these two things. So that's how the correlation matrix gets generated. And then we have a bunch of other tests for hypothesis testing or those kind of things that come into play. And so basically any summarization that we want to do over data, we need statistics for that. And also for data preprocessing, for instance, we want to normalize the data. That is another statistical operation that we want to apply. Normalization, standardization. So these are important from the point that we want We don't want our machine learning model to be worried about, because if it's a normal distribution of data, but the mean is shifted to one side or the other, then the ML model we don't want that to be as an input. We want the data to be as clean as possible, so that the machine learning model is able to make as is able to get fine-tuned as easily as possible. So that's again some place where statistics comes into picture. Now coming to encoding, the encoding part, for instance, we bucketize the data. So that is also a form of statistics data. That's called just data binning, and we can encode categorical data. Now we also have when we are training machine learning models, we have this concept of cross-validation, that there's a concept of overfitting, that given a small amount of data, the machine learning model can actually learn all the parameters or learn your entire data set and basically overfit it, saying that, but it won't generalize really well. It just learns, it does a root learning of your entire data set, because it's a small data as compared to the parameters that are available inside the model. And it is able to then give a very good performance on the training data set, so to say. We want the cross-validation. So cross-validation is a technique to avoid that. We hide some part of the data from training and then later on validate using cross-validation. So there are different kinds of approaches that are available for cross-validation. For instance, you would do k-fold validation, that you would train the model multiple times, hiding different parts of the data from the model and giving the rest of it for training. So as to we don't waste any data from, since we already have very small data set, we don't waste any data from not being used in training. And at the same time, we try to make sure that the model does not overfit. So all these techniques do come into picture. So these are the use scenarios where you need the knowledge of statistics to be with you. Now, coming to the concepts, the basic concepts are, I think most of us would know. Mean, median, mode are something that most of us get introduced with in school. Then we need to have a basic understanding of what variance means, what standard deviation means, and how they are derived, what covariance is, how it works, and how do we calculate that, correlation, percentiles, and a bunch of things. So that all those things come under basic statistics. Now, coming to little advanced things, when you are creating machine learning models, you create a bunch of different hypotheses, and you want to test them. And to test them, you need some statistical metric to be able to figure out that, okay, this is how well my hypothesis holds. So for that, there are a bunch of statistical tests. And you would need a basic idea of, so charts and plots, I think, are basic. Okay, I would not say basic. So we basically need charts to visualize data, to understand how our data is behaving, and or what's the pattern in our data that you want to find out. So visualization is a very important aspect when we are developing machine learning algorithms, because if we have ourselves an intuitive understanding of the data, that this is how the data looks like, and this is the kind of distribution in my data, then we can make much better decisions on the kind of features we want to create from the data, and what kind of algorithms we want to use from the data based on the data set that we have. And do we want to manipulate the, so for instance, in our example, the example of good customers versus bad customers, the percentage of bad customers might be very small. So how do we make sure that a machine learning algorithm is able to understand that we are more concerned with the small percentage of the bad customers that we have against the huge percentage of customers which are good. So to be able to do that, we again pre-process the data in some one way or the other to make sure that this is called class imbalance. We have a class imbalance. We have a very small number of bad customers in our data set. To do that, again, we apply some machine learning, some data pre-processing techniques, to make sure that class imbalance is omitted. And if not pre-processing, we apply something in the algorithm itself to make sure that it works. So again, those kind of things are again visualized much better using charts. And we also need to have an understanding of what central, how skewed is the data, what's the, so there's a central limit theorem and the concept of central tendency that we need to be aware of. And what do confidence intervals mean actually? Because these things are needed to understand the data as well as trying to make sense of the output. That this is how confident my model looks like to me, and whether I feel confident about the model that I can use this for my business or not. So yeah, that's mostly about statistics. To talk about different roles, I think it would depend on what you want to do. You would need to have an understanding of most of this, even if you are not really going to dive that deep into it. Because to make sense of things, you need to, so most of the metrics that are being communicated around are just statistical metrics. And you need to be able to make sense of those metrics. That, okay, this is how good of a hypothesis that we gave for our business is, or this is how confident the model that the team has developed looks like to be. So for those kind of things, you need to have a really good understanding of the statistical concepts if you want to move forward. So with that, I think we have covered all the topics. Now, I'll just again describe how, so basically how different roles basically assimilate for, and how important is mathematics for different machine learning roles. I have been trying to give that picture to you guys, but I'll just try to summarize it once again. So this is the entire spectrum basically of machine learning, that on one end we have ML engineers and on the other end we have ML researchers, and the product people are in another dimension that we have. So just talking about engineering to researching, we have data scientists in between and those kind and the middle roles where it's partially research as well as partial application. And based on where you are in this spectrum, you would need a different level of understanding for these concepts. And we've tried to give a summarization of what level of understanding we need. I've tried to give this at for every topic as well, based on the three major broad classifications that I did, but this is a more fine-grained classification of different machine learning roles that we have. So you can go through this and try to let me know if you have any questions on any of these things, and we can take them, I think, right now. Okay, before we take questions, I think we can quickly go through a bunch of FAQs. I think these are the most frequent questions that are usually asked at a beginner level or at a level where we are trying to get into machine learning. So yeah, this is a very frequent question that there are already several libraries available outside in open source world. Do I really need to know the maths of those things? I can't just use them off the table. Now, we can do that, but you won't be able to make the most of it. You might be able to pass your data through a already implemented scikit-learn function, a scikit-learn model. But to be able to actually milk it, to be able to tune it, you need to have an understanding of what's going on under the hood, what's going on inside the model, to be able to fine tune it, to be able to understand the behavior better. And we need to have an understanding of mathematics to be able to do that. Another question that we usually get is, are mathematical questions asked in ML interviews? I would say yes, very much so. Not just basic mathematical questions. I have seen scenarios where the industry asks you to, the interviewer basically can ask you to derive one level NLP, one level one layer MLP, derive the forward prop and the back prop for that particular model if we are going into that kind of a team. So we do need to have an understanding of what derivatives are, what gradients are, how do we use them in deep learning models and those kind of things. Okay, I think we have some really good questions from people coming in. One question is from Arjun Krishna. He says, when an engineer is using any ML algorithm from Python library, for instance, where is math needed? Is it helpful to know math behind it or not? Can't we simply adjust the parameters? So Arjun, so to say, you can work with without understanding the mathematics of underlying things. But again, as I said, you won't be able to milk the most out of those models. So when you're working in a production, in a business use case, or in a real world scenario, there is competition around you. You can't expect your things to just work out of the box. So that in case of so for instance, when we are doing constrained competitions, we are given a very good data set and we can work with it. But if we want to work with in real world, we want to milk the most out of the ML algorithms. So the Python libraries that you're talking about, there would be some tuning parameters that are available to it. And you can't really adjust those parameters just based on your intuition always. You need to have an understanding of what do those parameters mean? How do I start from? Where do I start from? So that obviously there is a search space that you create and you try to optimize it. But even to create the search space, you need to have an understanding that, okay, this is a good starting point and this is how I would want my model to be. So the architecture of the model, you would decide based on those things. So for instance, if you're using a decision tree or you're using a neural network, you would want to decide that how many layers you would want to have, how many nodes in each layer you would want to have, and those kind of things, and what activation functions you would want to have, what kind of loss functions you would want to pick. You can't just do that just picking something from Python package ready to go. It's important to know the underlying mathematics, that this is how these are the options available to me, and this is how they work. You can't just go about trying out all this stuff because there are a lot of permutations and combinations that are out there. So it helps to know mathematics to shortlist a few things. But that being said, you can obviously brute force everything if you have enough compute available. Coming to the next part, Priyanka Kumari has given a good questions. How important is the statistics for developing ML models in the real world? As I covered during the statistics part, I think I answered that. I'll answer that again. Statistics is pretty important when you're trying to evaluate the models. To evaluate the models, and as well as to figure out how the data looks like. So when you want to make sense of the data and make sense of the model output, those are the places where we really want to have a grasp over statistics that to evaluate different kind of things. Okay, let's cover the FAQs, remaining FAQs. So the next frequently asked question that I usually get is, if you're learning ML for managerial roles, do we still need to know maths? So I think I've tried to cover this throughout my presentation, that the kind of depth you would need for a managerial role, you still do need to know the mathematics, but at a very basic level, so that you can interpret the results and make sense of what is happening. What kind of problems the team is working with and the team is dealing with. Another question that I get is, if I have no degree in maths, can I still learn ML? And the answer is obviously yes. You can learn ML. You don't really need a degree to do that. It's not a certification that makes you eligible to learn ML. Anyone can learn ML. Yep, that's about it, I think. We can take a few more questions from the audience.
All right. All right. Hey, thank you, Siddharth. Thank you, Siddharth, for a wonderful talk. And everyone, please feel free to ask questions. And Siddharth, is there a question that you want me to answer so far? I can try to answer. All right, wonderful. There had been so much of okay, great. I will try sharing the screen. Okay, so all right. So we are done with this. Perfect. So everyone, yeah. So at CloudxLab, all of our content is accessible via a simple subscription, and you all right. It's pretty low cost, and here basically you can just, if you subscribe to CloudxLab, you get access to the content, access to the lab. Now, important thing about lab is you get big data tools, machine learning, big data tools like Spark, Hadoop, and other peripheral tools there, along with the machine learning, TensorFlow, scikit-learn, all the library is pre-installed for you. So you can basically do a lot of hands-on there. And there's a lot of content which is tightly integrated with the lab, whereby it evaluates whether you're doing well or not. So I can say that the CloudxLab subscription is something that will help you. And it would, right? It's not that the lab is only for the things that we have built. Anything that you want to experiment with, the lab is good. Though the lab doesn't have a GPU, but for most of your workload, this is sufficient. Many universities, many colleges, many edtech companies use our lab as well individually. So you get, and essentially, that's a good way to learn. And also we have very good discussion forum whereby you have like access to asking questions to expert like Siddharth or anybody. Like there are quite a few people who are there. So I would request everybody to be there. There are a couple of questions that I would like to go ahead with. And okay. All right. Although this has been answered again and again, that ML works on stats. What depth is required about the stats? So as Siddharth was saying, that you need to know the stats in order to interpret the outcome of machine learning, right? Machine learning model. Like for example, let's say you're working in a firm, right? And there is a vendor who has come to pitch you a solution. Now he's saying that, hey, our model is like 99% accurate. Okay. And then you ask like, what exactly is 99%? Is it accuracy? Is it precision? What is the distribution of the data on which it has been tested? Right. So this is common sense, but this common sense is not that common when you are asking questions to a partner, right? To a vendor or somebody. So this I have seen in past, that many people who have taken our AI for Managers course, for example, they get a brief introduction on the maths part. You get, you get to do the stats part, like what's a mean, median, distribution, and then what is skewing, how do you do the A/B testing, how do you do those kinds of, so the I think even though the statistics is needed for machine learning, but it's not like you have to do a degree. As Siddharth said, you don't have to do a degree in statistics in order to be good. Most of the statistics is fairly simple, and lots of things that you hear this keyword and then you get scared, right? Like, for example, you will hear something like stochastic, right? Stochastic. Now, stochastic sounds like a big word, but it essentially means random in very simple words. Similarly, you will see multinomial distribution. Okay, multinomial selection. Now, it sounds like a big word, but it can be expressed in a very simple way, like selecting few things from here. So the way I always approach the courses, or any course for that matter, is that I would start the course, whatever is there needed, like in all our courses, whatever is needed for the course, we have provided a complimentary courses for it. And like, for example, we realized that anybody who's getting machine learning engineering, they need to know Git, they need to know Python, they need to know basics of NumPy pandas and so on. We've included all of that as part of the course. So when you are taking CloudxLab subscription, you'll get all of that. Now, the other strategy is that you just jump into the course. If you get stuck, do a Google search on that particular keyword. If you are not clear about what does it mean by let's say median, right? You just look up. Though these are very simple example, but yes, just look up and then. So instead of going too much sequential, okay, I would say jump in, and whenever you get stuck, and then you look up, right? So that's something. One thing which I saw in lots of lots of discussions is that it's like easy to tell people, like when you as a learner go to an expert and like a professor or somebody, and then they say that you need to finish off these, you have to learn statistics, linear algebra, this, that, and then come back. Only then you are allowed to study. That's a wrong approach. My way will be just jump in case you get stuck, look up, and then keep moving. Okay. None of this is, none of the things, none of the ideas are so hard that a normal person can't deal with it. It's just that there'll be a knowledge gap, but you can just cover that knowledge gap in a couple of hours of research and you'll be able to move forward. But if you just keep sitting and worrying about that, okay, I have to finish this thick book, only then I'm allowed to do this. That's a wrong approach. That's a wrong approach. My way always have been just jump in, wherever you get stuck, look up and keep moving, keep moving. And otherwise you'll build this mental block that I'm not able to understand this subject because I don't know the fundamentals. Don't be in that loop. Just start. If you get stuck in algorithm, you basically look up. Like, for example, I'll give you a very good example, everybody. This is something close to my heart subject. So like somebody said that, okay, you need a background in calculus for machine learning. Yes, that's right. You need to know differentiation. But the amazing part for me was when I like talked to many experts who were many engineers who were good at calculus. And when I asked them that, hey, can you differentiate a Python function? Can you differentiate an image? Differentiate as in a derivative, first derivative, right? And what I found is that even those people who are very good and expert at calculus, they were not able to do it, okay? Because for whatever reason. Now, the important part is whether you are an expert or not an expert, you anyway have to look up each individual concepts. You anyway have to learn each individual concept. So there is no additional advantage people with a very deep technology, deep background on calculus are getting. So my suggestion will be, you anyway have to look up, you anyway have to read through this. So why not just go straight into the course? Whatever is needed there, it's already explained wherever, whatever is the basics. I hope I made sense to all of you. My explanation. Siddharth, does it make sense to you, whatever I said?
Yeah, definitely. I agree.
Okay.
It's not needed to have a complete grasp of things, but it's good to have knowledge of what are your options that are available, and then you can just brush them up whenever you need them.
Correct. Thank you. Okay, could you just explain how various roles you just mentioned differ with respect to jobs, the role platforms, and so on? Is vector calculus important for machine learning? I'll take up these two questions. I'll start with the question, is vector calculus also important for machine learning? Good question. So the entire book on vector calculus that I studied and during my college and all that, it was somewhat useful in the current knowledge. But what I realized that I had to anyway read through everything. Okay. So what exactly, when we say vector, what does it mean? It means it's a list of numbers, right? It's a list of numbers. Okay. So let's say you have one list of number and you have another list of number and you want to compute how different are these numbers, right? That's what is the main loss function about. When you are building recommendation engine, you have to, given the ranks of one set, you have to compare with the ranks of another, right? So in the sense that you need to know, let's say, what's a dot product, okay? Like, for example, to find the similarities between two vectors, you need to basically do a dot product and divide them by their absolute value, right? So that's like cos theta angle that you used to do, right? When you draw a triangle and you have two lines, A and B, and you want to find the angle between them, you do the dot product of those two lines, like AB cos theta equals A dot B. And you basically theta you can find out from there. So now the important part that I'm talking about is that, like, for example, we are doing the similarity between two vectors, like me as a person, my choice of things have been expressed as a list of numbers. And let's say Siddharth, his choice of things have been expressed as numbers. Now, we want to find out how similar are me and Siddharth. So we'll have to do a dot product. Now, this basic knowledge of what is dot product used for, how many things are there, that anyway you will get as part of the machine learning. Wherever needed, it is explained that this is what it is. Okay, so basic vector calculus or basic vector things are needed, not big deal, but it's not like you have to finish the book. Okay, just jump in, whatever is needed, you go back and look up. That's all. All right, that's all. And it's not that you should not build that mental block that you have to finish everything. Okay, you have to just get started. Wherever you get stuck, look up, and then that's how you move. Also, could you explain how the various roles I just mentioned, right? So so there are roles I think were mentioned earlier. I'll just go back. This one, right? So when you are building, let's say, a new model, new loss function, like, for example, if you take a look at like face recognition object detection model called YOLO, the mathematics looks hard, but when you look at it in a plain English, it'll be like simple. So while designing the model or researching on model, you might need a very good understanding of the algebra, calculus, right, and statistics, probability. You need really deep understanding of those. But as an ML engineer, you just need a good enough understanding. Okay, so now when it comes to the roles, let me also do a differentiation. So ML research is somebody who is publishing papers, who is trying publishing papers. Papers are two kinds of papers people are publishing these days. One, applied machine learning. Take a model, take a business problem, try to build the model around it, gather the data, and then do the prediction, and then you publish your research. Right? That's a kind of applied machine learning papers. For that, you don't need to be an ML researcher. As an ML engineer, you can do that. The other range of like papers are like research paper, where you are discovering new models or you are improving upon the existing model. So that's the role that ML researchers play on a larger scale. Now, a data scientist basically needs to know what machine learning, some part of the machine learning, and also data scientist as a title has been badly abused in past. It's been abused in the sense that everybody is called a data scientist now, right? many startups, they want to call people data scientists so that right, that way they can attract many people into joining even as a fresher. So data scientist is fairly abused term, so that's why in some companies data scientist role is like ML researcher. Some companies data scientist role is like data analyst. That's why we are saying medium to high and so on. Now, in case of the data analyst, right, you don't need to go deeper into algebra, calculus, but you need to know like the statistics. Like what does a data analyst do is that given, let's take a case of say Amazon, right? So Amazon, let's say you are trying to figure out which product or which A/B testing is making sense or not. So data analyst is supposed to look at the data and figure out, look at the data. So data analysts need to know like SQL and the other software skills like NumPy, Pandas, basic skills like NumPy, Pandas and SQL. But they need to be really good with the statistics so that they can create the tests. Data analysts might have to create tests and experiments and surveys and do the analysis of like biases and so on. So there are, because when you get the data, there are lots of biases in there that you have to deal with. That's where the probability and the statistics knowledge come into play. Now, data engineer, on the other hand, is responsible for translating raw data into structured data on a larger scale and transfer the data from one place to another on a larger scale. So they need to know, like they don't need to know too much here, but their software skills should be really good. Okay, I hope that answers your question, Ravi. All right. Do you want to add anything to that? I hope. Are you right?
Yeah, that covered it pretty well. That was a really nice explanation for most of the rules.
Perfect. All right. Any other, my teammate Sachin is also there in the chat. So Sachin, is there any other question that you want me to answer?
No, I think you have answered all the queries, and rest of the content is covered in the presentation.
All right. Perfect. Thank you so much. I'm really thankful to Siddharth, and I attended the whole session today. I learned a couple of more things, and yeah. So what I understood is that my priorities and Siddharth's priorities are very similar, and good. So. Wonderful, everyone. I stay connected with CloudxLab, and we will be having more such webinars, and as coming in the coming days. Our focus is more balanced, neither too much on the research side nor too much on just applied side. We are more about, you can say our focus is more like a machine learning engineer as a company. So we believe that if you understand the entire pipeline, that's how you would be able to do and grow in your career, rather than being very esoteric or very confined to a particular idea, right? So I think that's the reason why we have launched MLOps, why we have done system engineering and so on, because we're trying to do the entire pipeline, entire loop. And we want to do the applied part, because applied part is what improves people's career. Also, we as a company, we innately believe that everybody can learn, everybody can achieve great heights, and it's not only few people, and therefore we believe in imparting that knowledge. All right, so wonderful. Thank you again, everyone. Have a good day. Thank you, Siddharth. Thank you, Sachin. Perfect. Bye.
Thanks, Sandeep. Thanks, Sachin.
Thank you, Sandeep. Thank you, Siddharth, for joining.